In the second film of this series, the transonic range was described, in which the airflow round the aircraft is mixed, part subsonic, part supersonic. The dark green represents regions of subsonic flow, the light green supersonic. Shock waves are shown in red. This film is about the much more straightforward supersonic range, where the main flow everywhere is supersonic, shown, as before, in light green. To understand supersonic flight, it's necessary to examine the nature of supersonic airflow, which behaves more simply than subsonic. First, consider what happens when a single point is moving supersonically. Pressure waves sent out continuously at the speed of sound form a round cone, the Mach cone. The lines forming it are called Mach lines. The half angle of the cone is called the Mach angle, usually shown by the Greek letter mu. The size of this angle depends on the ratio of the point's forward speed to the speed of sound, that is, on the Mach number. At Mach 1, the Mach angle is 90 degrees. As the Mach number is increased, so the Mach angle grows smaller. A similar effect can be seen by dipping the point of a pencil in a fast-moving stream of water. Only the region inside the wave is influenced by the pencil point. The water outside this region flows on as though no disturbance existed. In the same way, the supersonic point can only affect the air lying inside the Mach lines, shown here in white. Ahead of the Mach lines, the air is undisturbed. Since all the disturbances coming from the point are infinitely small, the speed and direction of the airflow, shown here by white streamlines, don't change as the air passes through the Mach lines. But what if the disturbance is large? Such a disturbance is produced by a leading edge in supersonic flow. An oblique shock, the bow wave, is formed. How does the flow behave as it passes through such a shock wave? Consider first a diagram of a normal shock wave. This, at right angles to the flow, always slows it down from supersonic to subsonic. The speed is represented by the length of the arrow. Here's an analogy. This toy animal walks down a sloping board, faster down the steeper part, and then slower. Here's the same thing seen from directly above, supersonic, subsonic. If the whole board is now pushed sideways, the animal's path across the screen is a straight line which bends suddenly. In just the same way, imagine a uniform sideways velocity superimposed on the airflow. This will not be affected by the shock wave and will be the same on both sides of it. The resultant airflow is now like this, exactly as it was for the animal. It's now supersonic past the shock wave, but slower than ahead of it. If now the whole picture is turned round, so, nothing is changed. The shock wave is oblique to the airflow and has deflected it and slowed it down. Pressure always increases when velocity is lower. And if streamlines are drawn, they are closer together past the shock wave than ahead of it. The shock wave can be caused by a solid surface with a sharp corner. The streamlines are parallel to the surface. The surface may be the leading edge of a wing. This deflects the flow in exactly the same way. This supersonic wing section has another kind of sharp corner. Here, just the reverse happens. The streamlines move further apart, the speed increases, the pressure falls. After turning the corner, the streamlines are parallel to the new surface. This is called an expansion. How does it happen? Consider a streamline very close to the surface. The influence of the sharp corner will be felt along a mark line at the appropriate mark angle, just as the influence of the pencil point is confined to the region bounded by the mark lines. None of the streamlines will be affected until they reach this mark line. As soon as they pass it, they bend slightly and move further apart. The influence of the corner is at once felt along a new mark line, and the streamlines bend again, and so on. An expansion at a corner can be looked on as a series of tiny changes in direction, pressure, and speed. The expansion ends at the mark angle corresponding to the final speed and direction of the flow. So it is confined to a fan-shaped region between the first and last mark lines. Inside this region, pressure, direction, and speed change smoothly, unlike the shock wave case, where there's a sudden change in direction and pressure. But in both cases, supersonic flow wheels round to follow the new surface with little disturbance. Here it is obstructed and so slows down, whilst here it's been helped on its way, so it speeds up. Compare the behavior of subsonic flow round a similar corner, shown here in a smoke tunnel. The airflow slows down suddenly, and the pressure increases. The boundary layer separates and breaks down the streamline flow. So sharp corners like this are avoided on subsonic aircraft. Supersonic flow behaves much more smoothly and simply. Boundary layer separation is relatively unimportant. How do these facts about supersonic flow affect the design of actual aircraft? Here's a wing section which would give lift at supersonic speeds, a thin, flat plate. Here is the flow pattern. On the upper surface, the pressure is less than atmospheric, as there's an expansion at the leading edge and a shock wave at the trailing edge. On the lower surface, the opposite happens, and the pressure is greater than atmospheric. Here is the pressure distribution. This area is a measure of the lift. The center of lift is at the midpoint of the wing. Unfortunately, a wing like this is not practical structurally. Here's one answer: the double wedge. The thickness here is exaggerated. This missile has a double wedge wing. Here's an actual wind tunnel picture taken by Schlerin photography at Mach 1.8. Here is the flow pattern. The sharp corners on upper and lower surfaces couldn't be used on a subsonic wing because of flow separation. This is the pressure distribution. This area once more represents the lift, which again acts at the midpoint. Two arcs of circles go to make another possible section, the biconvex aerofoil. The thickness here is again exaggerated. After passing through the shock wave at the leading edge, the air speeds up gradually round upper and lower surfaces, and the pressure is reduced on both. Here's the pressure distribution. This area represents lift, which again acts at mid-chord. Here's a Schlieren wind tunnel picture. Both these aerofoils, double wedge and biconvex, combine the thinness and sharp leading edge needed for low supersonic wave drag with sufficient depth for structural strength. They apply only to straight wings without any sweep back. At a given angle of incidence, they both have the same lift coefficient. This is smaller at supersonic speeds than that of a subsonic aerofoil at subsonic speeds at the same incidence. At supersonic speeds, a high lift coefficient is not needed, as the speed is high enough to give the aircraft the lift it needs. But a low lift coefficient brings severe low-speed problems, high stalling and landing speeds. So very long runways and sometimes extra braking devices are needed for aircraft with these supersonic wing sections. Some missiles use straight wings without sweep back, with double wedge or biconvex sections. So do some supersonic aircraft. But as with subsonic and transonic flight, sweep back is very important in supersonic flight. Look again at the single point moving supersonically. The air is undisturbed everywhere ahead of the marked lines. But behind them, in the white area, the air is affected. Now suppose the point is in fact the wing route of this straight-winged supersonic aircraft. The air has no warning of the wing's approach. But what if we sweep the wing back until it lies within the white area? Now the air ahead is warned of the wing's approach. So, although the aircraft is flying at supersonic speed, the wing behaves as though it were subsonic. It can therefore have a subsonic section. Today, in fact, most supersonic aircraft are highly swept or deltas. These aircraft do in fact have very thin subsonic wing sections with high enough lift coefficients at low speeds to avoid serious stalling and landing troubles. Although some of them are so fast that they still need extra braking devices when landing. The higher the speed at which an aircraft is designed to fly, the more highly swept it must be, so that the leading edge remains inside the marked lines. But there are limits beyond which the aircraft becomes difficult to handle, both at low and at supersonic speeds. So the choice is between straight wings, usually short and of low aspect ratio for sufficient strength, or highly swept, or delta wings. What decides the planform of a particular supersonic aircraft? It's a compromise between many factors, a very important one of which is supersonic drag. Take a delta planform such as this. Plot its drag against Mach number. The curve is like this. A swept planform with the same amount of sweep will give this rather similar curve, while a straight wing, giving a similar landing speed, will give this quite different curve. The straight wing gives less drag at the higher Mach numbers than these particular swept or delta planforms. It looks as if below about Mach 2, the advantage for low drag lies with the swept shape. Or with the delta. While above Mach 2, the straight wing planform seems at first sight to be better. But drag can be reduced still further above Mach 2 by increasing sweep still more, provided the low-speed problems can somehow be overcome. Here's one possible solution for the future. Vertical takeoff. Here's another. An aircraft which has straight wings at low speeds and becomes highly swept for supersonic flight. Shapes like these may well be the supersonic airliners of the future.